Wah. Ulit dito ka sa aking cat.
Lima, dalawa lang.
Ayun.
Hindi pong Malboro.
Ay, ubos na ha.
Ay, wala na? Wala na, wala na.
Holy shit! Ay, nako. Hunter. Noo pa.
Hi everyone! Ayan, kalalapag ko lang dito sa Salt Lake City. Nasa hotel na ako. Hindi ako nakatulog at all sa biyahe. So, hihintayin ko pa si Jillian. Padating si Jillian from New York in about 2 hours. Naisipan ko mag-video para hindi lang ako antukin. First time ko sa Salt Lake. Nasa Utah ito. Bukas, papunta kami sa Park City, another city mga an hour away, dahil doon yung Sundance. Dito lang kami mag-overnight ngayon kasi si Jillian dadating gabi. So dito ka na siya hihintayin. Yung airport namin malapit lang sa hotel. So mag-what's it my bag ako. Yung dala-dala kong bag, ito, gift to sa akin ng Christmas. Sinubukan ko siyang dalhin. Okay naman siya dahil siya yung malaki. Malaki siya. Ito yung handbag ko kuno. Kailangan malaki para yung lahat na kailangan ko habang nasa aeroplano kasi long haul, nandyan na kaagad. Yung bag ko laging, parating malaki yung bag ko kasi maraming iba-ibang klaseng mga pouch. Yung pinakauna kong pouch, ito, lalagyan siya ng passport. So, nandito yung passport. Maliban sa passport, ito yung passport. Ayan, passport. Nandito din yung aking vaccine certificate. Kasi, although wala namang nangihingi, pero pasiguro lang na meron akong vaccine certificate. Yan yung una kong pouch. Lahat na biyahe, dala ko yan. Tapos, merong, parang yellow lahat sila. Ito yung smaller pouch. Ang laman ng smaller pouch ay breast powder. Ayan, Charlotte Tilbury yung dala ko ngayon. 2 lipstick. Ayan. Thank you sa mga nagregalo ito. You know who you are. Thank you. Tapos, meron din 2 lip balm. Kasi minsan, pag nasa loob ng plane, matagal yung flight, talaga nakaka-dry masyado ng lips. So, 2 lip balm yun nandito. Tapos, eye drops. Tapos, meron din ako, hindi ko alam kung bakit, ayan, nawawala. Ginamit ko. Wait. Saan ko kaya nalagay? Dito na iba yata yung nalagyan ko. Ginamit ko kasi nag-BabyRan ako kanina. Ayan. Itong dalawang to, lagi ko itong dala. Ayan. Deep Relief from Young Living. Ginagamit ko siya pag may early signs na magkaka-migraine ako. Tapos ito, nasabi ko na to before yung Aromate. Pinibili ko to sa very good friend ko si Mate. Iba-iba siya, pero yung favorite ko dito, yung Deep Z's. Ayan. Pag hindi ako nakakatulog, ito yung aking ginagawa. So, ito yung mga laman nito. Tapos, andito din yung Chinese. Okay, magbibigay. Ito daw yung ito,
狙いは取ったか。
Those people na gustong i-take advantage si VP Sara, they might have that agenda. So si VP Sara should be smart enough. She should be smart enough to recognize kung kailan siya ginagamit. Okay. Ito kasi sinabi ni Trillanes. Itong mga darating na buwan ay critical para sa survival ng Marcos administration. Pag umabot ng 2025 at nakuha ng mga Duterte ang mayorya sa Senado, magiging lame duck na sila, Marcoses, at alanganin na sila dyan. Okay. Oh wait, baba pa natin ng konti. Yan. Ilang hakbang na lang, pwede na siyang i-impeach anytime at uupo yung anak. Trillanes added. Ayan. Okay. Ito ngayon, mga kotsero. Agree ako sa punto na yung 2025 is critical. Agree ako doon sa punto na 2025 is critical. Bakit? Kasi si Martin Romualdez is stepping down. Bababa si Martin Romualdez. Pag bumaba si Martin Romualdez, sigurado at hindi, bumaba si Martin Romualdez at hindi pabor kay PBBM yung bagong magiging House Speaker. Delicads. Delicads. Kasi third term na to ni Third term na to ni Martin Romualdez. Kailangan na niyang bumaba. Term limits, remember? Ayan. So either tatakbo siya pa senador, pataas, o bababa siya. Either governor or mayor ng distrito nila kung saan siya nakatira. Which now leaves the House of Representatives very, very, very open. Si GMA, pwede siyang tumakbo ulit bilang kongresista. Meron pa siyang 2 term na natitira. Yan. Nakapagpahinga na pala siya noong 2019. So, 2019, 2020, 2021, 2022, tumakbo siya ulit bilang House of bilang kongresista ng 2nd District ng Pampanga. So, ibig sabihin, fresh na fresh ulit ang kanyang termino, si GMA. So, si Martin Romualdez bababa. Sure yan. Kasi naka 3 terms na siya. Si GMA, meron pang 2 terms. So, pwede pa siyang tumakbo bilang congresswoman sa 2025. Which means, may power vacuum. Pagbaba ni Martin Romualdez, may power vacuum. Sino ngayon ang magiging House Speaker? Kung hindi pabor yan kay PBBM, yari. Kung hindi pabor kay PBBM, yari. Kung pabor kay PBBM, okay lang. Pero kung GMA ang uupo, sigurado ka, hindi yan pabor kay PBBM. Sure ka na doon. Sure ka na doon. Kung si GMA ang uupo na House Speaker. Will she get the votes? We don't know. Probably. Magaling pumulitika yan si GMA. Magaling pumulitika yan. So mga kotsero, kung hindi rin kung majority ng papasok din sa Senado is yung sa 12 na papasok, most of them are Duterte supporters. Let's say 6 o 7 are Duterte supporters or DDS. May problema ka pa rin. Magkakaroon ka ng 2 klaseng oposisyon kung ikaw si PBBM. Meron kang oposisyon na galing sa Dilawan, si Risa Ontiveros, tsaka kung sino man yung papalit kay Coco Pimentel. Kasi si Coco Pimentel, last term na rin niya to eh. Kung sino yung papalit kay Coco Pimentel. At saka yung kabilang oposisyon na grupo ng mga DDS. Wherein kasama si Senator Amy Marcos kung may elect siya ulit. So may problema siya, si PBBM. Virtually mawawalan siya ng control sa Senate. At kung si GMA ang House Speaker, mawawalan siya ng control sa Congress. So, posibleng mangyari itong sinasabi ni Trillanes na magiging lame duck yung last 3 years ni PBBM. Kung hindi niya makukuha ang Senate at ang House. Like he has it today. Magiging lame duck siya. Isabi ng lame duck, wala. Wala kang magagawa, wala kang ma-accomplish, walang measures mo ang maisusulong, wala. Bakit? Kokontrahin ka ng Senado o kokontrahin ka ng House. Yung mga gusto mong batas, hindi nila isusulat. Walang mangyayari sa pagiging presidente mo. Yung budget mo, questionin ng questionin, pababa ng pababa. Lahat ng gagawin mo, questionin. Mahirapan ka. So, to some degree, agree ako dito sa sinabi na to na parte na to ni Trillanes. Which I think, kailangan na ngayon pag-ingatan. Kung gusto ng PBBM camp na mapanatili ang performance nila, kapangyarihan nila hanggang 2028, kailangan bantayan nila to. Kaya, very, very telling itong flex na to ni VP Sara. Yun ang konteksto na iniikutan yan. Yan ang konteksto iniikutan yan. 2025 elections. Sa flex na to ni VP Sara, pinakita niya, sinasabi niya, may isa na kami. May isang, yung Marcos, amin, yung isang Marcos. Meron ka pang bato. Meron ka pang bongo na tatakbo rin for the election. May Tolentino ka pa. Tatakbo rin yan for the election. Robin Padilla, na nandun na ngayon. So, meron kang sure na si Senator Amy is also running for senator at maganda ang kanyang performance sa surveys. So, meron ka ng 5. Number 1 daw, si Digong sa mga surveys for senator. So, meron ka ng 6. Nakakalahati ka na agad. Diba? So, minus, dadagdag pa yung iba. So, may 8 ka na. May 8 ka ng opposition out of 24. Diba? Papasok pa yung mga dilawan. Kung sino pa yung makakapasok ng dilawan. So, mahirap. Mahirapan si PBBM. And this is where ulitin ko lang yung, i-reinforce ko lang yung binanggit ko na noong nakaraan. Dito na ngayon, magkakasukatan ng ako, hindi ko masyadong pinapansin yung blood is thicker than water kasi it's irrelevant. Well,
New Jollibee Crunchy Chicken Sandwich. Crunchy, tasty, sarap in every bite. 59 lang.
It's really irrelevant sa usapan ng politika. So, hindi ko masyadong pinapansin yung blood is thicker than water na yan. Mas concerned ako sa political stability. Gaano magiging ka-stable ang ating bansa kung mangyari yun. Kung meron ka ng mas solidong opposition, solidified opposition to the administration. Kasi ngayon, medyo mahina. Mahina talaga ngayon ang opposition. Lakas ng House of Representatives. Lakas. Lahat ng bumangga, di ba? Diba? But, isang taon ka na lang. Yan ang binibilang ng kabilang partido. Naghahanda sila doon sa isang taon. Sa 2025. Tingnan natin ngayon kung anong magiging strategy ng dalawang kampo na to. This is going to be a very, very interesting election. Itong 2025. Defining moment to ng Marcos admin. Malay natin, baka mamaya, sa third year pala ni PBBM, biglang magkakaroon ng distab. Biglang magkakaroon ng impeachment. Hindi natin alam. It's possible. It's possible. Lalo na kung GMA nakaupo bilang House Speaker. I'm just saying, I'm just speculating because, GMA is not the biggest fan of the Marcos administration. It's a fact. So, let's see. This is going to be a very, very interesting 2025. Tayo, ang trabaho lang natin mga kochero, magmasid, mag-obserba, iboto kung sino ang tama. Tingnan natin kung ano yung magiging resulta nito susunod na araw pagdating sa ating politika. Pero matindi tong flex na to ni Vivi Sara. This is very telling of what's going to happen in the future, especially sa 2025 election. So ayan mga kochero, hanggang dito lang po muna tayo sa ating video. Okay, please don't forget to subscribe sa Coach Jared YouTube channel. And paki-follow na rin po tayo sa ating Facebook page at para lagi kayo updated sa mga ganap sa aking channel. And I'll see you all in our next Coach Jared Live. Alright, God bless. And see you next time guys. Bye.
Kapag nakikita ko ang mga ngiti nila, yan ang best part ng araw ko. Pero ngayon, may nawawalang ngiti na naman.
This Valentine's Day, give Toblerone, the thoughtful gift.
The enigmas encircling our cosmos are exceedingly intricate and demanding. Nonetheless, the James Webb Telescope is spearheading transformative strides in space exploration. In a momentous breakthrough, the James Webb Space Telescope identified numerous colossal, unidentified entities lurking nearby in our cosmic expanse. This startling disclosure delves into the mysterious entities constituting 95% of our universe. What roles do these perplexing entities play, and how will they augment our comprehension of the cosmos? Join us as we unveil how the James Webb Telescope has spotted 400 unknown objects traversing through space. You've probably heard about the Hubble telescope, a marvel that bestows incredible vistas and insights into the cosmos. However, it now has a successor, the James Webb Space Telescope, or JWST for short. Since its launch on Christmas Day in 2021, this technological marvel has been delving into the farthest recesses of the universe, unveiling its ancient secrets. The JWST signifies a new epoch in space exploration, delving deeper into the cosmos's mysteries than ever before. Distinguished from the Hubble, it excels at probing the infrared segment of the electromagnetic spectrum, allowing it to peer through cosmic dust clouds that often obscure celestial objects from our view. The JWST's true distinction lies in its advanced technology, featuring high-resolution and high-sensitivity instruments, enabling it to detect objects too aged, distant, or faint for the Hubble to capture. By capturing cosmic signals, the JWST offers unparalleled insights into the universe's birth, galaxy formation, and the enigmatic realms of dark matter and dark energy. Dark matter, with its unseen but substantial gravitational influence, remains a cosmic puzzle. Yet the JWST continues to unveil more details about such cosmic entities. How does it discern these hidden objects in space, and what implications does it hold for the cosmos's future? The JWST's primary mirror, an engineering marvel consisting of 18 hexagonal segments coated with a thin layer of gold, spans an expansive 26.3 square meters. This allows it to collect a remarkable amount of light, generating detailed celestial images. Positioned at the Sun-Earth Lagrange 2 point, approximately 1.5 million kilometers from Earth, the telescope enjoys an unobstructed view of the cosmos, over 4 times the distance to the Moon. While this extensive distance poses challenges for maintenance and repair, unlike the Hubble, it also shields the JWST from Earth's atmosphere, reducing interference and providing clearer, more precise observations. Unlike the Hubble, which received several servicing missions, the JWST is situated significantly deeper in space. Moreover, the advanced infrared instruments on the JWST are invaluable for studying the atmospheres and compositions of gas giant exoplanets, offering insights into the formation and evolution of planetary systems beyond our own. Fortified with a sun shield, a massive protective layer roughly the size of a tennis court, comprising 5 ultra-thin membrane layers, this shield acts as a formidable defense against the sun's intense heat and the radiations emitted by Earth and the Moon. Weighing around 6,500 kilograms, the telescope's advanced design and meticulous engineering ensure its smooth operation in the harsh space environment, allowing it to fulfill its ambitious mission of peering deep into the cosmos. With these capabilities, the James Webb Space Telescope has made significant progress in unraveling the universe's mysteries. Recently, it unveiled hundreds of ancient galaxies, potentially among the first members of the universe. These findings provide fresh insights into how the initial galaxies and stars formed, shedding light on the cosmic processes shaping our current cosmos. However, the JWST isn't solely a window to the past, it's also a key to foreseeing the cosmos's future evolution. Essentially, it serves as a cosmic time machine, enabling us to witness the universe's early light and track the progression of galaxies through time. In a remarkable revelation, the JWST has disclosed a dusty ancient book of the universe, revealing hundreds of remarkably old galaxies that existed merely 600 million years after the Big Bang. This astonishing discovery stems from the JWST Advanced Deep Extragalactic Survey, JADES, a vast international project. Harnessing the JWST's remarkable observational capabilities, scientists focused on two celestial areas, one directed towards the Ursa Minor constellation and the other towards the Fornax cluster. The revelations were staggering. More than 700 youthful galaxies, previously unseen, emerged through the lens of the telescope. Kevin Hain, an assistant research professor at the Stewart Observatory in Arizona and one of the lead authors, likened this breakthrough to the opening scenes of a cosmic life movie. These galaxies, in their early stages, initiated the elemental creation process, a precursor to the complexity we witness today. During the universe's infancy, within the first 370 million to 650 million years, a surprising 717 of these nascent galaxies were identified, a higher number than initially anticipated. This implies that over 700 galaxies existed when the universe was still very young, comparable to a handful of elementary school kids suddenly evolving into an entire school district overnight. These galaxies each span thousands of light years across, similar to our Milky Way's width, already forming complex structures and giving birth to stars in multiple clusters, as if sprinting right out of the gate at full speed. Before this revelation, the earliest observable galaxies seemed no more than faint smudges. However, with the JWST's capabilities, these smudges transformed into extended objects, revealing visible structures similar to a blurry photo sharpening into focus. A fascinating phenomenon to witness. The specific regions where these young galaxies were discovered are collectively known as Goods South, a segment extensively studied by major space telescopes like the Hubble Space Telescope, the Chandra X-ray Observatory, and NASA's retired Spitzer Space Telescope. Despite the comprehensive scrutiny by various high-profile telescopes, an astonishing 93% of the galaxies spotted by the Webb telescope during the JADES project were completely new discoveries. The universe was harboring secrets, awaiting our technology to reach the level needed to unveil them. Before this enlightening discovery, astronomers primarily observed the celebrities of the early universe, which were the bright, extreme galaxies. However, the JWST's recent findings introduce us to the average inhabitants of the cosmos, the everyday galaxies navigating through an infant universe. Curiosity might lead one to ponder how the cluttered, dusty universe of the past transformed into the clear, transparent cosmos we know today. Scientists have been contemplating a crucial phase known as the Epoch of Reionization, thought to have started roughly 400,000 years after the Big Bang, a period when the universe was a newborn, opening its eyes to the world. During this phase, the first generation of giant stars emerged, massive and millions of times brighter than our sun. Their ultraviolet light kick-started reionization, transforming the opaque universe into the transparent one we see now, a monumental process continuing for about 1 billion years post-Big Bang. However, some astronomers propose another contender, supermassive black holes. They suggest these giants, like the one in the heart of our Milky Way, might have influenced the cosmos by aiding the escape of ultraviolet radiation from galaxies, shaping the universe's evolution more significantly than previously thought. Surprisingly, the JWET isn't collaborating with just one team. Another group from the JADES program is studying galaxies that existed between 500 to 850 million years after the Big Bang, an action unfolding just 5 to 8 minutes into our cosmic movie. Within these moments, the universe has already matured, offering new mysteries to solve. This team might have cracked the cosmic code, uncovering answers to long-standing questions about the universe. According to Ryan Ainsley, a researcher at the University of Texas leading this study, they're deciphering the impact of galaxy formation on the broader universe's composition. In the early universe, galaxies had a more chaotic approach to forming stars, energetic and unpredictable youngsters. This adds another layer to our comprehension of how our universe took shape over time. The team's investigation into early galaxies for signs of star formation, focusing on how starlight ionized the gas within these galaxies, revealed fascinating insights into the universe's evolution at that time. They stumbled upon the intriguing discovery that 1 in every 6 galaxies showed extreme line emissions in their spectra, indicating a bustling production of stars in the youthful galaxies. The torrents of ultraviolet photons from these early stars played a crucial role in driving cosmic reionization, transforming the universe from a dusty, opaque expanse into the clear cosmos we see today. Yet, these galaxies don't stand alone in captivating revelations. Scientists have identified the oldest intricate organic molecules in the cosmos. These molecules, resembling those in Earth's smoke and soot, were discovered within an early galaxy that existed when the universe was merely 10% of its current age, known as polycyclic aromatic hydrocarbons, PAHs. These complex molecules are common on Earth, found in oil, coal deposits, and even city smog. Unlike simple molecules like water or carbon dioxide, PAHs are intricate, sizable structures with dozens or hundreds of atoms. Remarkably, these molecules were intricately assembled and present in the universe during its infancy. Widespread in space, akin to grains of sand on a beach, these complex organic molecules often cling to tiny dust grains in the cosmic expanse. They offer valuable insights into interstellar gas cooling rates, functioning like miniature thermostats that influence the temperature of the gas between stars. Understanding these molecules becomes crucial for astronomers seeking to comprehend the intricate processes shaping the cosmos. For years, astronomers yearned to study these molecules in distant galaxies formed during the universe's youth. However, the historical limitations of telescopes hindered the detection due to sensitivity and restricted light wavelength ranges. Enter NASA's latest powerful space observatory, the JWST. Using this cutting-edge tool, Spilker and his team identified complex organic molecules in the galaxy SPT 041847, an astounding 12 billion light-years away. The revelation that these molecules were found in a galaxy so distant implies they existed when the universe was a mere 1.5 billion years old, a fraction of its current 13.8 billion years. It's akin to receiving a message sent across the expanse of space, arriving at our doorstep after a journey spanning 12.3 billion years. Albert Einstein's theory of general relativity, illustrating mass's ability to distort space-time, serves as the theoretical backdrop. Gravitational lensing, a phenomenon where a massive galaxy cluster acts as a magnifying glass, played a pivotal role in the discovery. The JWST, a revolutionary space observatory, surpassed its predecessors by detecting these molecules in just an hour, making the search appear effortless. The JWST not only confirms the existence of complex organic molecules in ancient galaxies, but goes further by offering detailed insights into their specific locations within a galaxy. In the case of SPT 041847, researchers observed a non-uniform distribution of these molecules across the galaxy, a mystery that remains unsolved. Compiling these discoveries, Spilker proposes that galaxies might have experienced an exceptionally accelerated pace of formation. For instance, the galaxy they studied, despite being only a tenth of the age of our Milky Way, boasts a comparable mass and has produced similar amounts of carbon and oxygen. This vivid analogy illustrates how early galaxies were fast-tracked in their evolution. Interestingly, these complex organic molecules were previously thought to be closely associated with star formation. However, the JWST's data challenges this assumption. Spilker's team found regions rich in these molecules devoid of star formation and vice versa. This unexpected observation underscores the universe's ability to surprise us as our understanding deepens. These intriguing findings emphasize the JWST's role in unraveling cosmic mysteries. Spilker expresses excitement about the telescope meeting astronomers' expectations, foreseeing these insights propelling the astronomical community's collective knowledge forward. Looking ahead, he's curious about exploring even younger and more distant galaxies, pondering whether it's plausible to discover a galaxy where these large molecules simply haven't had enough time to form. He's also eager to understand why these molecules appear in certain regions of galaxies, but not in others. It's a waiting game to delve deeper into these cosmic puzzles and unearth further revelations. The age-old question of whether we are alone in the universe has also intrigued humanity for centuries. Despite the countless celestial entities sparkling in the firmament, the possibility that Earth is the sole harbinger of life remains uncertain. While researchers have identified over 5,100 exoplanets in nearly 3,800 systems, confirming extraterrestrial life or identifying habitable planets remains a challenge due to vast distances. Rohan Naidu, a young astronomer at Harvard University, stumbled upon yet another groundbreaking discovery that sent shockwaves through the scientific community. Using a special algorithm, Naidu examined NASA's first deep field image, a picture capturing light that has journeyed billions of years through space. This image offered not just a view of celestial bodies, but a glimpse into the distant past, showcasing a spectrum from red, which is the oldest light, to blue or white, the most recent ones. On that fateful evening in July 2022, Naidu's algorithm identified a galaxy named Z13 that defied convention. This galaxy, almost 13.4 billion years old, shockingly challenged the Big Bang Theory's timeline. According to existing models, the universe, born from a single point in the Big Bang, transitioned from hot, dense particles to form hydrogen and helium. Stars emerged 150 million years later, eventually coalescing into galaxies over 1 billion years. However, Z13's existence merely 400 million years post-Big Bang contradicted this theory. Z13's discovery triggered a myriad of similar galaxies, unsettling the foundation of the Big Bang theory. Advocates of this theory were troubled, as evidence suggested a different cosmic structure and origin story. The mystery extended to dark matter and fundamental forces, where scientific assumptions collided with the James Webb Telescope's revelations. The unprecedented insights questioned not just the Big Bang's timing, but the universe's very beginnings. Another anomaly in the form of the mysterious Schrödinger's galaxy, SEER 1749, emerged as it existed 200 million years after the Big Bang, seemingly out of sync with its cosmic surroundings. This galaxy challenged measurements, emphasizing the limitations of current methods. Redshift, a key factor in measuring cosmic distance, revealed a surprising array of galaxies with ancient origins. Hubble's finding of a galaxy with redshift 11 was groundbreaking, but James Webb's data surpassed this, unveiling galaxies with redshift values reaching 20. These revelations startled astronomers, prompting a frantic effort to reconcile JWST's observations with established cosmological models. With galaxies like Glass Z13, estimated to be 13.5 billion years old, and SEER's 93316, possibly even older, it challenges our understanding of cosmic chronology because these ages are significantly older than the estimated 13.8 billion years since the Big Bang. In addition to unveiling ancient galaxies, JWST's recent breakthrough included the detection of exoplanets. The telescope's ability to analyze minute changes in starlight and spectra allowed it to detect exoplanets with unprecedented precision. LHS 475b, an Earth-sized rocky exoplanet orbiting a red dwarf star, became the first planet analyzed using JWST. Scientists are now deciphering its atmospheric composition, marking the initial step in potentially identifying life-supporting conditions on distant planets. The limitations of JWST in seeking the edge of the present-day universe are quite clear. It captures light that has traveled for varying durations across space before reaching us. For instance, the light we see from our neighboring stars in the Centauri system takes around 4 years to reach Earth. Consequently, the telescopic images portray celestial objects as they appeared in the past, making it impractical to view the existing universe's outer limits. Moreover, the universe's expansion, a fundamental concept since the Big Bang, remains under scrutiny. Dark matter, a mysterious element shaping the universe's structure and expansion, continues to baffle scientists, and JWST's expected contributions to understanding dark matter are eagerly anticipated, potentially filling crucial gaps in our cosmic comprehension. Nevertheless, the telescope's first strikes into probing dark matter are still pending, leaving astronomers eagerly awaiting potentially paradigm-shifting results. Dark matter, despite its hidden nature, is deemed an integral cosmic constituent, forming the foundational structure of the universe. However, its defiance of conventional physics puzzles scientists, raising concerns about our current understanding of the cosmos. The spatial implications of JWST's continued findings are profound. A mismatch between observations and established theories could necessitate a complete overhaul of our understanding of the universe's origins. As scientists grapple with these mysteries, they're left pondering the accuracy of existing theories and the prospect of redefining our cosmic history. The known observable universe stretches approximately 13.5 billion light-years, a fraction of the universe's total size. This observable cosmos within JWST's viewing radius measures about 28.5 gigaparsecs. Yet the universe's actual size remains a grand mystery, with an estimated event horizon, a boundary marking our observational limit at 16 billion light-years. While JWST's capabilities are impressive, its range is finite. Beyond this limit lies a domain obscured from our current technology. Nonetheless, astronomers remain optimistic about reconstructing cosmic events through advanced computer simulations. Questions surrounding life on other planets, the mystery of dark matter, and the universe's edge remain unanswered. The JWST's mission unfolds against this backdrop of cosmic intrigue, promising transformative insights into the universe. As we navigate these cosmic riddles, the James Webb Telescope stands as a scientific successor to Hubble, made to delve deeper into the universe's origins, study distant galaxies, and analyze extrasolar planets in unprecedented detail. The telescope, designed specifically for infrared astronomy, holds the promise of unlocking secrets hidden in the earliest reaches of our cosmic history. And gradually, it's reaching there. Thanks for watching. Remember to subscribe to our channel, Save Earth Now. Make sure to check out another of our interesting videos by clicking on the link appearing on your screen right now.
That the angle to be measured is minuscule, a tiny fraction of 1 degree. It's smaller than the angle spanned by Abraham Lincoln's nose on a penny in San Francisco, viewed from New York. Because the angle is so very tiny, it can't be measured by any one telescope. But Reed's team has a solution.
We take 10 radio telescopes that are spread across the continental U.S. and to Hawaii and to St. Croix in the Virgin Islands. We use these telescopes simultaneously, and we synthesize in the computer a telescope that has the diameter of the size of the Earth. That gives you incredible angular resolution.
Using this technique, Reed's team determines that Cygnus X1 is 6,000 light years away.
With the new distance we got, 6,000 light-year distance, we're able to determine that the mass is about 15 solar masses, easily a black hole.
40 years after it was identified as a possibility, Cygnus X1 is now widely accepted as the first confirmed black hole.
It's an understated paper, and the fact that my name was on it and Louise Webster's was on it did us a lot of good in our careers. I think as a result of this discovery, I got offered a permanent job, and it was a great celebration for the family. So it worked out very well for me, as well as getting the intellectual satisfaction of solving a problem.
So finally, after years of speculation, we have a real black hole. Not only that, but a black hole that's blasting out X-rays and has a companion star. If we could visit in my imaginary spaceship, what would we see? The distance to Cygnus X1 has been established at 6,000 light years from Earth. And its mass is 15 solar masses, or 15 times the mass of the sun. And Cygnus X1 is surrounded by an accretion disk, a disc-shaped cloud of gas and dust outside its event horizon, the point of no return. As gravity pulls matter toward the black hole, the cloud starts rotating, just like water being pulled down a drain. Within that accretion disk, particles closest to the black hole whip around at half the speed of light. It's like a giant particle accelerator in space. But why does it emit X-rays? As those particles race around, they collide, which heats them up to millions of degrees. When they get that hot, particles blast out X-rays. And it's those X-rays that first led astronomer Paul Merton to investigate this black hole nearly 5 decades ago. And there's something else about Cygnus that's different. It has a companion star. This blue supergiant star orbits the black hole once every 5.6 days. It orbits so close to Cygnus X1 that the black hole strips material off the star and pulls it into the accretion disk. Some of that material will cross the event horizon and get swallowed up, but not all of it.
Some of the stuff actually comes back out before ever entering the black hole. Kind of like a toddler eating. Half the pasta ends up on the floor, half of it maybe on the ceiling, and some of it in the mouth.
One of the most striking and enigmatic features of Cygnus X1 is its enormous jets. These beams of particles and radiation stream outward from Cygnus's north and south poles, perpendicular to the accretion disk. There's still a lot we don't know about these jets, but they are tightly focused and extremely powerful, blasting out at nearly the speed of light and extending well beyond Cygnus.
When gas gets to these high temperatures and produces the light, there's also a little bit of a magnetic field that forms around them. And we don't understand exactly how, but these magnetic fields help collimate these massive outflows from black holes. Powerful hoses, if you will, that just spew matter out.
So that's Cygnus X1, if we could see it up close. A growing, feeding black hole with huge jets, blasting particles way out into the universe.
They're almost these breathing, fire-eating demons, if you will. They flicker, they burst. It's a very violent fireball, very active.
What was once a bizarre mathematical curiosity has now become quite real. After decades of skepticism, scientists now accept that burned-out corpses of large stars can trap light inside them, warp space and time around them, attract matter, and accelerate it to mind-boggling speeds.
Black holes seem like such a radical idea that we shouldn't accept it. But bit by bit, the evidence for black holes has gotten stronger and stronger. And we've seen these amazing things.
At least 20 black holes have been found in our galaxy. X-ray binaries like Cygnus X1. And there are probably millions more of these massive stellar corpses in our galaxy alone. Still, a stunning surprise awaits. Everything astronomers think they know about black holes, and much of what they believe about the universe itself, will be upended by a shocking discovery. The revelations begin when radio telescope surveys of the sky detect mysterious hot spots emitting radio energy.
They were coming from what looked like stars.
Because these objects resemble stars, but were discovered through radio signals, Astronomers name them quasi-stellar radio sources, quasars. But are they stars or not? The first step in investigating them is to figure out what they're made of. To do that, astronomers analyze the electromagnetic energy they emit. Every element has a unique spectral fingerprint. For example, carbon, helium, hydrogen. These lines reveal the chemical makeup of a star. But the spectrum of a quasar turns out to be incomprehensible.
They looked at it and it was gibberish. It didn't look like there were any emissions from elements that they knew.
What are they missing? There has to be a clue somewhere. Finally, in 1963, Caltech astronomer Martin Schmidt finds it, hiding in plain sight. Buried in the quasar spectrum is the fingerprint of hydrogen.
He noticed something familiar, but it was in the wrong place. The fingerprints of hydrogen had been shifted way off to the red.
It was hard to spot because the spectral lines of hydrogen were radically shifted toward the lower frequency end of the spectrum. And that could only mean one thing. The quasar is moving away from us at fantastic speed. But astronomers have never before seen light shifted to such an extreme. Like a familiar sound shifting too low to understand. The light from quasars has shifted to such a degree that hydrogen is unrecognizable. This extreme amount of shift means quasars are racing away from us at blinding speed. The reason? It's the legacy of an event that occurred almost 14 billion years ago, the Big Bang. The beginning of our universe. And ever since, the universe has been expanding, carrying with it all the objects it contains, including quasars.
No one had ever seen anything moving away at that high speed. This made this object the furthest away thing that had ever been seen, which meant the thing itself had to be so luminous, and you had to account for that.
2 billion light years away, putting out the energy of 1 trillion suns each second. What could possibly create that?
No one had any idea what could be powering these things. Where could all of this energy come from?
If you work out through calculations, it can't be chemical energy. They knew it couldn't be nuclear energy.
There's no way a quasar could be a star. No amount of nuclear fusion could produce that much star power.
The only engine that could possibly put out that much energy is gravity.
Gravity. In everyday life, we can overcome gravity easily. But when concentrated to an extreme by a black hole, gravity is overwhelmingly powerful. A handful of scientists start wondering, could quasars perhaps be powered by gravity engines? What if the energy blasting out from quasars is coming from bright accretion disks around black holes?
To produce that kind of energy, that kind of brightness, it has to involve a black hole.
But not just any black hole.
Whatever was the source of the emission from the quasar had to be massive. How massive? Well, millions or billions of times heavier than the sun.
Millions or billions of times heavier than the sun. Cygnus X1 is only 15 times the mass of the sun. The black holes powering quasars are an entirely different category of black hole. Supermassives. And they seem to be located in the centers of galaxies. But what about our own galaxy? Could there be any supermassive black holes closer to home? The center, where any supermassive would be found, lies in the direction of the constellation Sagittarius, the Archer.
Now, Sagittarius isn't just any constellation. It's in the direction of the center of our own Milky Way galaxy. But since we live inside the Milky Way, we can't see the galaxy the way a space traveler would. But I can use my trusted imaginary star machine to show us the galaxy from the outside. Our home is a spiral galaxy, hundreds of billions of stars drawn together into a gigantic disk. It's wide, about 100,000 light years across, but it's relatively thin, only about 1,000 light years thick. And the whole spiral slowly rotates. Our solar system is here. And here, 26,000 light years from the Earth, is the center, which we see in the direction of Sagittarius. In this dense center, there are millions of stars and lots of dust and gas. So that's the view of our galaxy from the outside, thanks to my imaginary technology. But since we live inside the Milky Way, when we look towards the center, we're looking through much of our own galaxy, which means it appears to us as a band of stars and dust across the sky, a Milky Way.
Deep inside this band of stars and dust, could a supermassive black hole be lurking?
We're getting now.
In the 1990s, astronomers grow determined to solve the mystery, to peer through the murky Milky Way and learn what, if anything, is at its center. One of them is Andrea Ghez. Ghez takes on a daunting challenge. She will try to track individual stars orbiting the center of the galaxy.
The essence of this experiment comes from watching stars orbit the center of the galaxy. So you want to find the stars that are as close to the center of the galaxy as possible, which means that I want to get access to the largest telescope I can possibly get my hands on.
And that means coming here. Summit of Mauna Kea, a dormant volcano almost 14,000 feet above the beaches of Hawaii. High altitude and low humidity make this the ideal place for astronomy. The instrument Ghez uses is Mauna Kea's Keck Observatory, one of the largest in the world. But despite its size, Keck has the same problem as all telescopes on Earth: atmospheric distortion.
Think about looking at a pebble at the bottom of a river. The river is moving very quickly, and your view of that pebble is distorted.
Like a river, the Earth's atmosphere is constantly changing, bending light like a funhouse mirror. To compensate for this, Keck pioneers the scientific use of a declassified military technology called adaptive optics. First, they shine a laser into the sky, creating an artificial guide star. The turbulent atmosphere distorts the guide star. But the computer knows what it should look like and adjusts the telescope mirror accordingly.
So if you look at yourself in the circus funhouse mirror, you look completely distorted. And the goal of the adaptive optics system is to introduce a second mirror that's the exact opposite shape and make you look flat again.
Buried deep inside the telescope, the deformable mirror changes shape up to 2,000 times a second to reverse the atmosphere's distortion.
And it has allowed us to take the sharpest images ever obtained of the center of the galaxy.
The sharpness of those images allows Ghez to make out individual stars near the center, a huge advance in astronomy. She begins recording their positions in 1995.
And every year since then, we've taken an image. Just take a picture.
Putting those annual snapshots together creates a time-lapse movie of stellar orbits. And what those movies reveal is astounding. The stars are whipping around the center of the Milky Way at phenomenal speeds.
These things are moving at several thousand, up to 10,000 kilometers per second, or 10 million miles per hour. They're really hauling.
To go that fast, the stars must be orbiting something extremely massive.
The mass that we infer is 4 million times the mass of the sun.
What could be 4 million times the mass of the sun, yet be completely invisible?
That is the proof of a black hole.
And not just any black hole, a supermassive, silent and sleeping, right in the center of our own galaxy.
In fact, this is the best evidence to date that we have for the existence of supermassive black holes, not only in the center of our own galaxy, but anywhere in the universe.
Supermassive black hole, 4 million times the mass of the sun, in the very center of our own Milky Way galaxy. From a cosmic perspective, it's right next door. And it raises a profound question. There are billions of galaxies out there. If ours has a supermassive black hole at its center, and if quasars are found at the centers of their galaxies, what about the others?
Are there black holes at the centers of galaxies? If they are, how common are they? We simply didn't know.
Could astronomers ever hope to find what lurks at the centers of other galaxies, millions of light years away, as GES did in our Milky Way? It would take another innovation in astronomy to make that possible.
And liftoff of Space Shuttle Discovery with the Hubble Space Telescope. Window on the universe.
When the Hubble Space Telescope starts delivering clear images of distant galaxies, a team of astronomers gets to work. They become known as the nukers because their focus is galactic nuclei, the centers of galaxies. One of them is Todd Lauer.
Step one, we take a picture of a galaxy with the Hubble Space Telescope. It shows us where the stars in the galaxy are, tells us the structure and exquisite resolution.
The key to finding supermassive black holes is to learn how fast the stars in the galaxy are moving. Galaxies outside our own are much too far away to measure the speed of individual stars. But by analyzing the way light is shifted from blue to red at different points in the galaxy, astronomers can put together an average speed of stars orbiting the center. It's accurate enough to create a replica in a computer.
The second step, where the real work begins, is to try to model the observations. We actually do that by building models of galaxies in the computer.
It's known as Schwarzschild's method, developed by Princeton astronomer Martin Schwarzschild, son of Carl Schwarzschild, whose mathematics first described the possibility of black holes.
Martin Schwarzschild's trick was he would actually build up a model of the galaxy that not only had where the mass was, but it also had how the stars were moving.
For each galaxy they investigate, the nukers painstakingly build a computer model, and then using trial and error, adjust the parameters of mass and velocity, trying to make the model match the original observations they got from the Hubble.
And we say, let's try a star here, let's try one over here, let's go around this way, let's have this one go around that way. And we do this thousands and thousands of times until we build up a library of how stars can orbit these galaxies. Success is when observations of the model match the observations taken with the Hubble Space Telescope.
But that doesn't happen. The models are missing something.
We try it again and again and again, all with no black hole yet, and say, gee, we really can't get the observations explained by the model.
Only when they add an enormous invisible mass at the galaxy's center does the model match the Hubble observations.
Almost always, we have to put in a black hole descent. We can't match the observations without a black hole in the model.
Of roughly 36 galaxies that the nukers investigate, virtually all of them require a supermassive black hole. And since then, other observations have made us even more certain that supermassives and galaxies go together.
Every galaxy we've looked for one, we have found a supermassive black hole in its center.
It's a stunning revelation. Supermassives, once an entirely unexpected category of black holes, may be common. Not only at the center of our galaxy, but of all galaxies.
Take galaxy M31, also known as the Great Andromeda Galaxy. It's 2.5 million light years away. On a clear night, you can see it from Earth. But even with the Hubble Space Telescope, we can't make out precise details of its center. Still, we're pretty sure there's something extremely massive hiding there. What if we could take a closer look? What if we could visit a galaxy far, far away? As we enter the outer part of Andromeda, we're still too far away to see what's lurking at the center. But we can make out a dense cluster of stars in the core. And that could be a sign that there's a giant black hole nearby. Billions of years ago, it would have been surrounded by gas and stars and other small black holes. The black hole may have powered a quasar, feeding madly and blasting out blinding radiation. Over hundreds of millions of years, it would have consumed all the available gas and the closest stars. These days, it's relatively quiet, but it has some distinctive features we've never seen before. First, it's colossal. If it were dropped in our solar system, Mercury, Venus, Earth, and Mars would all be trapped inside the event horizon. That's big, but it's nothing compared to the sheer mass, 100 million times the mass of the Sun. And the destruction won't end there. Jupiter won't last long. The gravitational field of the supermassive will grab hold and swallow it whole. Eventually, Saturn will suffer the same fate. The outer planets might survive, but in cold and dark orbits.
This black hole rotates rapidly, distorting and dragging the fabric of space-time. Like all black holes, the event horizon is completely featureless. Remember, there's nothing there. It's just a boundary that conceals the interior. But the accretion disk can tell us a lot about what's going on. That's the fiery ring of gas and dust around the black hole. Imagine if we could release a swarm of autonomous robots to explore the accretion disk. The disk is spinning at an incredible speed, as much as half the speed of light. If Jupiter moved that fast, it would complete its entire orbit in a few hours. The region around the black hole is a cosmic tornado. Now our swarm is caught in the whirlwind too. They're like tracers, dropped into the storm to map the movement. The middle robot can send us images. It's following the leader like a race car speeding around the track. From here, the extreme warping of space-time around the black hole plays crazy tricks on our eyes. It looks like there's one accretion disk whipping around the equator and another arcing over and under the poles. But that's an illusion. The black hole's extreme gravity bends the path of light emitted behind the black hole and makes it look like the accretion disk is both above and below.
There's actually nothing around the poles. It's just the passing light rays.
That's gravitational lensing again.
Drawing much closer to the event horizon, the gravitational lensing would become so extreme that one of my robots could look straight ahead and eventually see its own back, the light forever trapped in an eternal circle. So that's our tour of the supermassive black hole at the center of the Andromeda Galaxy. Pretty amazing. Also amazing, nothing in the mathematics led scientists to imagine that black holes could get that big. As strange as they are, ordinary stellar mass black holes were at least predicted by theory. Supermassives are a complete surprise.
For the stellar mass black holes, people thought about them from a theoretical perspective. And then we found them observationally. The supermassive black holes, the story has been inverted. We actually found evidence of them observationally first. And now we're working on the theory of how did these things come into being.
We already know that stars can collapse to create ordinary black holes, but supermassives are bigger by many orders of magnitude. Cygnus X1 is 15 times as big as our sun. The supermassive at the center of our Milky Way is 4 million times as big as our sun. The one in the Andromeda Galaxy is 100 million times as big as our sun. And it's not the biggest, not even close. There are supermassives 10, even 20 billion times the mass of our sun. How is it possible to make such gigantic black holes? Could supermassives have come from collapsed stars? That seems very unlikely. We don't know any stars billions of times bigger than the sun.
We know about black holes you might get from a dying star. They have several times the mass of the sun contained within them, but millions of times the mass of the sun. If that's the case, a dying star cannot have possibly made it.
So do these supermassives, millions or even billions of times heavier than the sun, somehow just grow, packing it on like voracious giants?
The wild thing about black holes is that they feed. They're constantly devouring anything that comes within their sphere of influence, so they grow.
But how exactly do they grow? What do they eat, and where do they find it?
We believe that black holes grow by accretion of gas. And the way this works is that you have a lot of gas around in the center of a galaxy, and this gas would then assemble and form an accretion disk.
The accretion disk is made up of hydrogen, helium, and other elements in a gaseous form. The immense gravity of the black hole pulls the gas in toward it. As it swirls around, it orbits closer and closer to the black hole, and the feeding begins.
The stuff in the inner regions would get slowly pulled in, sped up, will reach the event horizon, and then that's it.
Whatever gas crosses the event horizon disappears forever. The black hole has absorbed that material.
So it actually adds to the mass of the black hole.
So this is one way a black hole can grow, gradually nibbling gas and dust.
But it's not the only way. Cygnus X1 has been slowly stripping material off a nearby star, a process that will likely go on for thousands or millions of years. But what if a black hole could rip an entire star apart in just a matter of years or even weeks? That would be a very violent event.
and a team of space explorers is on the lookout.
Roger, copy.
This
Ready
is
for a
the
briefing.
Operations Control Center for a space telescope.
Ivy 5x5, how may? We show beginning of track at 0330.
The Chandra X-ray Observatory.
Copy, machine data. Roger, lead 16 minutes, 1-6.
Orbiting up to 86,000 miles above the Earth, Chandra takes high-resolution images of objects that emit X-rays. This is one. A short-lived, extremely violent event called a transient, which fascinates James Guillochon.
Supernovae, the destruction of planets by their host stars. I'm just fascinated with destroying things for science.
James is investigating a mystery discovered by a colleague, Da-Sheng Lin. This blur on James's screen is actually a massive sudden burst of X-ray energy, caught by accident.
This little smudge popped up in the background of this image, and given its great distance, it's actually tremendously bright.
Could it be a black hole caught in the act of being born in the violent collapse of a huge star? A supernova. Perhaps. But the intense radiation released by supernova would only linger for a few months. So how long has this mystery object been blasting out X-rays? To find out, they look at images of that same part of the sky taken at earlier dates. 2015, 2011, 2008, 2005 July, 2005 April. No X-rays detected. But the X-rays are there just 3 months later in July. And the powerful, bright signal has continued for more than 10 years. From July 2005 to the present. Far too long to be a supernova. So what could it be? A black hole that's not feeding is quiet and completely dark. It won't show up on any telescope. But a black hole that is feeding is different. When it feeds, it blasts out X-rays. So could this be a black hole that's suddenly begun devouring something big?
What effect will this have on anything that comes near? What would it do to a star that wanders too close? Well, it will flay a star, layer by layer, ultimately devouring the entire star.
Unlike Cygnus X1, this is no mere nibbling. This is a 10-year feeding frenzy. A massive black hole devouring an entire star in a cosmic blink of an eye. It's the result of a chance collision, when an unlucky star wanders too close and the black hole's extreme gravity actually rips it apart.
The gravity from the black hole will progressively get stronger and stronger as the star gets near. And at that point, the star will begin to deform.
It's called tidal disruption. It's similar to the way our moon's gravity easily moves all the world's oceans. The tides caused by a black hole would be billions of times stronger and much more violent.
You have these events where a star could be ripped apart by the black hole. So you would see sort of a plume of light from the last gasp of the material in the star.
But there is a chance for some part of the star to escape, as James illustrates.
As the star is elongated by the black hole's tidal forces, it will essentially be feeding the black hole at the same time as half of it is trying to escape. So everything above this point approximately will have the chance of leaving the galaxy. It's moving that rapidly. And everything below this point will fall back onto the black hole and eventually be consumed by it.
So this is another way for a black hole to gain weight. Unlike the slow, steady nibbling of Cygnus X1, this black hole is devouring most of an entire star in one gulp.
But whether a black hole feeds suddenly by swallowing half a star or steadily through accretion, astronomers still face a problem when they try to understand how supermassives got so big. The timing problem.
The trouble begins with the very oldest supermassives, quasars. Those very bright, very distant, and ancient objects first discovered in the early 1960s.
The conundrum was when we started finding these quasars, very bright quasars, very early on in the universe.
They're giving off so much energy that they have to have very massive, supermassive black holes at their center.
But quasars are extremely far away, which means they're part of the very early universe, which began nearly 14 billion years ago.
Bright quasars, 600 million years after the Big Bang, a fraction of today's age.
And they're enormous.
So billion solar mass black holes, these behemoths, had to be in place when the universe was about 550 million years old.
Now you have a problem because you have to grow something really big, really fast. And you are bumping up against sort of physical limits.
Whether a black hole is nibbling or gulping down its meal, it turns out that accretion, how black holes feed, has a speed limit.
Named after English astronomer Arthur Eddington, the Eddington limit will not allow a black hole to feed too fast because of the light blasting out from its own accretion disk.
Light has a pressure. So photons can impart a force on something. We see this in winds from stars. Light is pushing out gas. So there's a limit to how fast you can feed a black hole before its own luminosity quenches its own growth.
So given the speed limit, how did early supermassives, quasars, get so big so fast? Could there be a way to bypass the speed limit entirely?
The problem is still time itself. How do you grow them to 1 billion times the mass of the sun? What are the conditions that you need for that kind of growth?
Some scientists are now asking, what if there's a way to create a black hole that's already much more massive from birth, giving it a head start?
If there was a physical mechanism that would allow you to make a black hole seed, which was much more massive from the get-go, then the timing crunch is not as much of an issue and the growing problem is not as acute.
The answer, some believe, is to create a black hole directly from a cloud of gas, a scenario called direct collapse. It starts with gas clouds made of hydrogen, helium, and other elements, the same raw materials from which stars are born.
The denser clouds will start to collapse under their own gravity. And as they collapse, parts that are more dense will collapse more quickly. And so what happens is the cloud fragments.
New Jollibee Crunchy Chicken Sandwich. Crunchy. Tasty. All that set up in every bite. New Jollibee Crunchy Chicken Sandwich. 59 pesos lang.
Those fragments continue collapsing until the hydrogen atoms within them begin to merge. Nuclear fusion begins and stars are created. But what if a giant gas cloud collapsed without making stars?
We realized that there are a set of physical conditions that would allow you to form a very large gas disk prior to the formation of any stars. So this gas disk starts getting unstable. That would allow the mass to sort of flow into the center very, very rapidly and make a very massive black hole.
It's something we've all seen in nature. From tornadoes to bathtubs, a vortex, but on a supermassive scale.
If you're in a bathtub and you pull the plug out and you see the water flowing in a vortex very fast down to the center, that's exactly what happens.
Direct collapse might be a way to create very large black holes early in the universe from enormous gas clouds, completely skipping the star stage. Because they would be so large already at birth, these direct collapse black holes would have a head start, helping them to quickly grow into the enormous young supermassives we see in the distant universe.
You could potentially have these direct collapse black holes. So black holes whose original masses, seed masses, the initial masses, are about 10,000 to maybe 100,000 times the mass of the sun, and that they form from the get-go with that mass.
Direct collapse may explain how enormous early supermassives got their start.
But there's another fundamental question about supermassives. What is their role in the universe? Is their existence just a matter of chance? Or are they connected in some larger way to the very structure of the cosmos? Supermassive black holes don't exist in isolation. They seem to live in partnership with galaxies.
Collections of millions, billions, or even trillions of stars bound together by gravity. Galaxies are the fundamental building blocks of our universe. So are the supermassive black holes at their centers somehow fundamental to their very existence?
We now just assume every galaxy, even ones we have yet to confirm, will have a supermassive black hole in their center.
It could be that instead of simply being oddities, that they are a key component to galaxies, a key component to the universe.
We've come in a very short time to realize that they likely inhabit the centers of all the galaxies. And that can really only happen if there's some symbiotic relationship between the evolution of a galaxy and the supermassive black hole in its core.
What could that relationship be? One intriguing clue relates to size.
The bigger the galaxy is, the more massive the black hole appears to be. So these black holes at the center seem to know about their larger scale environment.
So which comes first, the galaxy or the supermassive black hole? It's not that simple. It appears they somehow grow in tandem.
It's hard for one to form first and affect the other. So today, we think that whatever formed one had to form the other as a byproduct of that process, and that there has to be some feedback mechanism between the black hole and the galaxy that keeps the growth of the two in lock sync.
The way galaxies grow is by forming new stars from clouds of hydrogen gas.
Gas is essentially the fuel for star formation, just like gas is the fuel for our cars. And so if you run out of gas, you run out of new stars.
So are supermassive black holes somehow interfering with star formation?
When a black hole is growing, a tremendous amount of energy is being liberated and sent out into the galaxy. And so we think that some of that energy goes to warm up gas. And gas that's too warm will not form stars anymore.
Creamy aroma, now cream of white, great taste cream of coffee.
The heat produced by a growing black hole makes it impossible for stars to form nearby.
And so one way that a growing black hole can influence its host galaxy is by quenching the star formation.
In effect, the growth of the supermassive determines whether or not its host galaxy grows or stagnates.
They have a kind of eating phase and then a quiescent phase. So they seem to be involved with the formation of the galaxy in that way, and then stabilizing of the galaxy at the same time.
So these mysterious supermassives may actually control the building of the universe. not so much by their size, but by the way the energy they generate shapes galaxies.
By mass, if you count up all the black holes in the universe, the tiny ones as well as the supermassive ones, the ultramassive ones, black holes are nothing. However, energetically, how much power the galaxy gets and at what time as it assembles seems to be dictated by the central black hole. So they might well be the key players in the universe.
In the next 2 years, NASA plans to launch the James Webb Space Telescope. Humanity's most powerful telescope ever, the James Webb is designed to look in the infrared, allowing it to see farther back in time than Hubble, getting a look at the first stars and galaxies that formed after the Big Bang. Hopes are high that the James Webb Space Telescope will help solve many of the remaining mysteries about the earliest supermassive black holes.
The James Webb Space Telescope is tuned specifically to observe the early universe when galaxies were being born that could give us deeper understanding of how you end up with a supermassive black hole in your galaxy to begin with.
Technology is moving really fast, and as a result, we have really fundamental new views of the universe. I think we are really living in a golden era of astronomy.
And the James Webb Space Telescope isn't the only new development that promises to solve some of the mysteries around black holes.
I believe have infrared components.
A group of scientists led by Shep Doleman is now attempting the impossible: to take a picture of a black hole.
It's interesting that we can say something about the accretion flow near the black hole at all.
And if some of this linear behavior survives, maybe we'll have a way of interpreting it.
The project is called the Event Horizon Telescope.
So it depends on when those... The basic goal of the Event Horizon Telescope is really to see the unseeable. It's to bring into focus something that science has told us for many, many years is precisely something we can't observe, the black hole.
Their primary target is Sagittarius A star, the supermassive in the center of our Milky Way galaxy. They're using a global network of radio telescopes.
We need good weather at 8 different telescopes all around the world, and that is a tall order.
But if black holes are invisible, what exactly do they hope to photograph?
What we're trying to photograph really is the shadow. So as this gas around the black hole swirls inwards and actually hits the event horizon, it leaves a silhouette, a very well-defined shadow on the surrounding light. So really it should look like a donut with its very well-defined hole. And that's the picture that we're after.
If I convert that into frequencies, I get a 2 pi square there.
The team has conducted their first observing run and is processing the data now.
And you're saying the velocity...
It's hoped that these new technologies will give us an unprecedented view of black holes in our universe. But there is one new technology that is already delivering results. And that brings us back here to LIGO, a key player in the black hole drama, to an idea that took root way ahead of its time: gravitational waves.
With general relativity, his theory of gravity, Einstein predicts that when an object moves, it can create ripples in space and time, an actual squeezing and stretching of space itself. One of the holy grails of 20th century physics was to detect these gravitational waves.
That was not easy to do with general relativity because all the effects that you could think of were infinitesimally small, very, very difficult to measure.
The thinking was, if gravitational waves could be measured, it would confirm Einstein's prediction. And there could be an added benefit. It might also prove the existence of black holes and help solve the mystery of how supermassives grow. But how to detect gravitational waves? In 1970, the problem caught the attention of a young experimental physicist, Ray Weiss.
Polydent, may strong kapit, gum comfort at food blocker. Bibig mo nang nagsabi, mag-Polydent palagi.
Ray had the perfect background to hunt for gravitational waves. For decades, he'd been working with more familiar waves, sound waves.
We were immigrants, we were German Jews, and a lot of our friends were very, very interested in music.
Ray devoted himself to coaxing every subtle nuance he could out of recorded music.
Those records had a terrible problem. When the music was loud, it sounded wonderful. When the music was real quiet and slow, what you heard was this shh, like that, a hissing noise. And that was so annoying.
The lessons he learns trying to eliminate noise in recordings will pay off later when Ray turns his attention to detecting gravitational waves.
You have to understand how a gravitational wave does its dirty work.
As a physics problem, gravitational waves are not unlike sound waves.
Suppose the wave comes from something that is in some way moving and oscillating.
A sound wave compresses and expands air. A gravitational wave compresses and expands space and everything in it.
If a wave came through the Earth, it would cause space to expand momentarily and then contract again. It keeps doing it. It's this thing that goes blip, 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 right along like that.
So how to measure the extremely tiny expansion and contraction of space? Ray's idea was to use light. Send a beam of light from one place to another and measure the time it takes to get there. That's how the exact distance to the moon was calculated, bouncing a laser beam from the Earth off a mirror left behind by Apollo 11 astronauts. From the duration of the round trip, scientists could determine the distance. Ray came up with an ingenious design for an instrument that uses lasers and mirrors to detect the faint expansions and contractions of space that would be caused by a gravitational wave. It's called a laser interferometer. It works by firing a laser into a splitter. Half of the light continues straight ahead towards one mirror, while the other half is sent towards another mirror. The distant mirrors bounce the light beams back, where they rejoin at a photodetector. If the distances the two beams travel are exactly the same, the system is designed so the two beams cancel each other out. The detector sees nothing.
You've set the trap to measure the gravitational wave. Now comes a gravitational wave that's coming, let's say, at this structure.
If a gravitational wave passes through, it briefly changes the length of the arms. The light beams no longer arrive back at the same time to cancel each other out. A gravitational wave hits, light appears at the detector. The trap has sprung.
That's the basic idea. It's a very straightforward measurement.
A clever idea and simple in principle. But the devil and the Nobel Prize lie in the details. The difference in length between the two arms would be tiny beyond imagining.
How tiny? We'll take the size of an atom. It's less than that. Go down by a factor of 100,000. That's the nucleus of an atom. It's less than that. It was 100 times below that. So we're talking about really itsy bitsy teeny weeny. I thought it was crazy. I think everybody's initial reaction to the idea was, this is going to be impossible.
In 1973, Kip Thorne puts his skepticism on the record in a classic textbook, doubting it will ever work. But Kip has never heard Ray Weiss explain his plan in detail. And when he does,
we spent the whole night talking. And so I said, no, it's very possible. And within no time at all, 20 minutes, maybe half an hour, Kip was solidly understanding this thing. And he says, yep.
And I ate crow the rest of my career because once I had talked with Ray about it in detail, I decided I would spend a large fraction of the rest of my career helping the experimenters.
But it will take 40 years and enormous sums of money to bring Ray and Kip's vision to reality.
Getting LIGO funded was extremely controversial. Hundreds of millions of dollars to detect a signal that had never been seen before. There were many people who feared that LIGO would suck the money out of the room. And so there was a lot of controversy. What everybody could agree on was this was extremely difficult.
With such a sensitive instrument, one of the biggest challenges is Ray Weiss's old hi-fi nemesis, noise.
Ground motion, the seismic motion of the earth, acoustics noise, sounds, everything would tend to move that mirror.
Turns out, even the emptiness of a total vacuum creates a potentially crippling problem. At subatomic distances, the weird randomness of the quantum world causes a ruckus in the mirrors.
This quantum noise is due to quantum fluctuations. These mirrors are doing what an electron does inside an atom. They're jiggling around.
Exquisite sensitivity, extreme vacuum, hundreds of thousands of electronic circuits. LIGO is one of the most complex instruments in the history of science. And as a final means of eliminating false signals, they build not one, but two complete installations. One in Washington State and another in Louisiana.
And so the LIGO designers did it right. They designed more than one detector, separated from one another by great distances, so that if you detect something in one and not in the other, then, go back and check your electronics. Check to see if it was April Fool's Day and somebody didn't just tweak the knobs.
Early fall 2015. Both locations are operating, but the first official science run has not yet begun. They're still testing. In the early hours of Sunday, September 14th, 2015, a scientist in Louisiana makes a fateful decision.
The one up on
Robert Schofield has been working all weekend, doing final calibrations.
Alrighty, let's take a spectrum.
He has one last test.
So let's see where this computer is getting its power.
But it's late, and the equipment is not cooperating.
It was about 4 or so in the morning, and we still had about another hour of work to do. And we were like, yeah, things aren't working so well, and I'm really tired. Let's not do this last hour or so of work.
They call it a night, and 40 minutes later, in the silence of their inactivity, they open the door to history. A powerful gravitational wave rumbles through both detectors, Louisiana and Washington. Had Robert Schofield worked 40 more minutes that night with the instruments in test mode, a signal that had been on its way for 1.3 billion years would never have been recorded.
I like to say, one of my biggest contributions to LIGO has been my laziness that day.
I got an email from somebody here saying, hey, you look at this place on the web. I looked at that, and I said, holy.
It was so strong that you could see it by eye in the data. It was too good to be true.
But it was true. In fact, it was loud and surprisingly clear.
And it just sang at you. The stair was standing up.
The signal lasted less than a second. But in that briefest of moments, it delivered a cosmically profound message more than 1 billion years in the making, proving the existence of black holes.
So what we saw in the signal involved oscillations of the mirrors that were slow at first, became faster and faster and faster. And this was precisely the kind of behavior that you would expect from gravitational waves caused by two black holes going around each other, spiraling together.
Two massive black holes, one 29 times the mass of the sun, the other 36 times the mass of the sun, whipping around each other hundreds of times a second, finally completing their act of mutual destruction by merging, creating a single, larger black hole of 62 solar masses. The violent merger converts some of the mass into an apocalyptic release of energy beyond anything ever before witnessed.
The collision, in effect, creates a veritable storm in the fabric or the shape of space and time. As though you had taken 3 suns, you had annihilated them completely, converted it into gravitational waves. The power was 50 times higher than the output power of all the stars in the universe put together, in a fraction of a second. But the most powerful explosion that humans have ever had any evidence for, with the exception of the Big Bang.
Since that very first signal in September 2015, LIGO has detected several more collisions of black holes. In October 2017, Ray Weiss, Kip Thorne, and LIGO's former director Barry Barish received the Nobel Prize. The LIGO discoveries prove that black holes can merge. One way they can grow bigger quickly.
More and more evidence of these merging black holes tells us there are a lot of these stellar black holes around that they can find each other and merge.
And the discovery opened an entirely new way of observing the universe.
We've always thought of astronomy as an observational field where we are looking at radiation. We are seeing things. But this is not radiation. This is something much more fundamental. These are sort of fundamental tremors in space-time itself. We can now hear the universe.
For the first time, astronomers have simultaneously seen and heard a cosmic event.
In August 2017, LIGO detected gravitational waves from a collision of 2 neutron stars.
Black holes are empty space, but neutron stars are dense, dead stars that can crash together and light up the skies.
When telescopes and satellites around the globe pointed in the direction of the sound, the world saw fireworks in an explosive collision and afterglow. Possibly, the collision resulted in the creation of a new black hole.
But unless we observe the formation of a black hole, there is much we will never know. Because so much about black holes is irretrievably out of our reach, we can never know where they came from, what's inside, or their history.
But we can imagine their future. the number of black holes in the universe is increasing, and they're getting bigger. Stars collapse, black holes feed and merge, new ones form.
Could it be that one day everything will end up inside them and they will rule the universe?
Untold trillions upon trillions of years after this happens, and the last bits of matter cross their event horizons, black holes themselves may radiate away and vanish from this reality.
Their mysteries are many, and we're just starting to unlock the secrets of these strange, powerful places.
But one thing is certain, black holes will continue to intrigue us, tantalize us, and challenge both our science and our imaginations.
Welcome to the dark side of the universe. On the hunt for the ultimate cosmic monsters. While scientists scan the heavens, advanced computer simulations reveal the strange power of the black hole. Venture beyond the point of no return. To nature's ultimate no man's land.